first question I'm going to ask you is this. Explain to me or give me some hints or some ideas about the difference between a t-distribution and the perfect normal curve. So what's the difference between the t-distribution and the perfect normal curve? What do you think? Ideas? Okay, good. The t-distribution is more varied because of the sample size. True. Very good, because of n. Now, question is, why do we have to use t-distributions instead of getting to use the perfect normal curve? Why can we not just say, oh, it's perfectly normal, yay? It has to do with it being a sample issue. It has to be with this. Has to be because of the sample issue. So here it is. If you have the standard deviation of the population, then you can use z-scores and you can use the perfect normal model. And you can use the perfect normal model. Okay, but that's the deal. That's the thing that we don't have, because you don't have, in most cases, we have the sample standard deviation. So this is the reason that we have extra variation, and that's the reason that we have to use t-distributions as opposed to the normal curve, okay? All right, so that's the reason for that. So just kind of clarifying it, keeping that in mind for you. So now, we skipped over the assumptions and conditions yesterday. For one, they're actually pretty much the same, except for one additional idea I'm adding to you today. And yesterday was really important you understood the idea of t-distributions. I didn't want to give you too much to digest at one time. So here comes this part. Furthermore, I'm kind of going to have to save this interpretations of the intervals for tomorrow. This was something that still overall I was not happy with on the last test. So we're going to spend a little time really working on this tomorrow. Okay, so here we go. Assumptions. Random, stated random or assumed a representative sample. Does that sound familiar? Is it changed or is it the same? It's the same, yay. Okay, so independent. We want to have our sample size be less than 10% of the population. So what about that? That's no different. That's the same. Okay, here we go. For large enough. Let's first, there's really 3 situations happening. Okay? All right, so let's look at this situation number 1. N is greater than 30. Yay! N is greater than 30. So, guess what? T-distributions can be used, because if you use sample standard deviation, they are safe to use, even if we are told that the population, sorry, it needs to be population, is skewed. Okay, that's nothing new. That is the central limit theorem. That's what that central limit theorem is saying. So let me remind you of a picture that we used to do. Remember that yellow screen we used to have where if you have the parent population is just totally jacked up, then if you drop down samples that are large enough, then the average of those samples are going to eventually form what? A normal model. Okay. So this is saying if the sample size is large enough, then we're going to have a normal model. And in this case, it's approximately normal because of the sample standard deviation we are using, regardless of the parent population. Okay. Again, that's what the central limit theorem is saying. We will drop down a normal or approximately normal regardless of the parent population if it's large enough samples. Okay, so that should be nothing new. That's a refresher course. We're good. We've talked about that before. No problemo. Now, here we get smaller samples. N is less than 30. So now we've got some issues to address. But we've done this before. We said, wait, there's hope. If it's small, then I can still be okay if only what? Correct. So in this case, it's the same. I can say that the sampling distribution, I'm allowed to use a T model, T distribution, if it is stated that the parent population follows this normal model. Then I've been saved. Yay! So let me show you a picture of that. If N is less than 30, that is worrisome. But this can still, the sampling distribution of averages can still, average of, all these different things, can still be considered normal if what it came from was the normal model. Okay. So if you've got a problem here, you can overcome the problem if it's told to you that the parent population is normal. Then yay, we're okay still. All right. Here is the new part for today. Here it is. Big star right here. This is the new situation that we have to learn how to address. This is a situation where we have a small sample size. And gosh darn it, it does not say that the parent population is normal. Curse you, problem. Okay? So we can fix this issue if we can feel comfortable that the mean is not being impacted by multi-modes like bimodal or trimodal mini bumps on the picture. If it is not skewed, and if there are no outliers, because that is critical. Those are the things that are going to screw up your mean. So if I can look at my data and come to a reasonable conclusion that it's unimodal, somewhat symmetric, and there are no outliers, then voila, it's okay to then say nearly normal model applies. So let's read this here. For smaller samples that the population is not stated to follow a normal model, the data can use, you're allowed to do our T distributions if you show that the distribution is unimodal, somewhat symmetric, and there's also actually no outliers. That's also important. You can check this by making a histogram. That's what we're going to learn how to do today. It actually is easier to make a histogram by hand because the calculator puts in weird funky bin sizes and decimals and stuff, and so we're actually going to find it much easier to do this histogram by hand. I'll show you this normal probability plot tomorrow. And so you know that you're really only going to be able to make this histogram if you have been given individual pieces of data, such as this down here. See? So you don't really anticipate having this problem or having to check this issue unless they're giving you a way to check the issue. They're either giving you the data to make a histogram, or maybe they give you a picture of a histogram, and that could happen also. Okay, so upon you then drawing a histogram, and next to the histogram you say, it is unimodal. You have to consciously, you have to write this down so that your grader or your reader is aware that you have checked this situation. It's somewhat symmetric. And no outliers. And again, what is the purpose of making these observations here? So that I feel comfortable that what? Well, I do not want the mean to be getting messed up by the multi-mode skewed data or outliers, okay? So if my data looks roughly those things, then I'm okay. And my conclusion of everything is that the nearly normal model applies. These are not perfectly normal, so you have to stress that it's a nearly normal model. Okay, so let's move on. Here we go. Example 1. Thomas Lane is a busy street that passes through a residential neighborhood. Residents there are concerned that vehicles traveling on Thomas Lane often exceed the posted speed limit of 30 miles per hour. Well, the local police sometimes place a radar speed detector at the side of the road, and as drivers or as a vehicle approaches, this detector displays the vehicle's speed to its driver. The police hope that the drivers will slow down if they are reminded of their speed. Have you ever seen one of those off to the side? It starts, okay. I always wonder which one's me, you know, but anyway. Okay, so the local residents are not convinced that such a passive method is helping the problem. They wish to persuade the town to add extra police patrols to encourage drivers to observe speed limit. So to help their case, I mean, if I'm on the city council, it's going to cost money to add these extra patrols, so you better have convincing evidence that this average speed limit's higher. But anyway, so to help their case, they had a resident stood where he could see the detector and recorded the speed of 23 randomly chosen vehicles passing at a randomly chosen time and day. Do these data give local residents evidence that the average speed of the cars going through the neighborhood is actually greater than the posted speed limit? Okay, so my first question to you is, how do you go about this? Is this a hypothesis test you need to handle, or is this a panic model where you need to make an estimated interval? We need to make a conclusion and have evidence of something. So then that leads you to what? I think it's a test. Correct. That's the kind of wording that would lead you to think you need to do an interval would be, okay, how much above the speed limit do you think that they are? Or what is your approximation of the average speed? Estimate the average speed. Okay, that would be an interval. Then you'd get a range. Okay, so here we go. Here is our data. Let's do a phantoms model because that's a test. And so the first thing we need to do is a P, which is a population parameter. So what is our population parameter? What is the population we are going to be making an inference about just from this one little sample? Okay, so we are going to infer about the average speed of, it's always good to emphasize population here, that you know you're going to infer about an entire population. So I'm going to make sure you know I'm making an inference about all cars driving on Thomas Lane. Now, how should I notate that? What letter should be used? A mu, because this is a population average. Okay, so that's the P. What's the H? Okay, our hypotheses. Null hypothesis is mu equals 30 miles per hour. The alternative that we are wondering if we have evidence is mu is greater than 30 miles per hour. Okay, so we've done P and H. What's next? The A. Assumptions. They are our favorite thing to do every time we run a test. Okay, so here we go. What's the first part of the assumptions? All right, random. What do you have to say about that? Sounds like they were trying to say, you know, imply that this was representative because they were randomly chosen cars on a random day at a random time. Okay. Independent. What am I going to say there? Okay, is it less than 10% of all cars? Of all cars driving on Thomas Lane. Okay? You need to be clear about the population that you're pulling from. All right, what's next? are large enough to see if we got something nearly normal going on. And we go, oh no, 23 is not greater than 30. Yikes. Okay, so, oh wait, there's hope. What could happen? Okay, do they tell us up here that we got normal model of population? Oh, curse you, problem. Okay, so now I have to do a what to fix that? Okay, so now we're going to do a histogram. So here we go. I'm going to kind of teach you how to do that. All right. First of all, you have to label. If you don't label, then it's going to say, you fool. That's wrong. You just lost points. Okay, so let's make sure we label. This is going to be miles per hour of Thomas Lane cars. And we're kind of going with these are ones that are moving, not just sitting there being parked. Okay, and so then we've got number of cars. We're making a histogram, and so we're kind of counting the frequency of these things. All right. Now, you need to determine the bin width. You need to kind of check it out of, how much data do you have? How much span do you have? And so the first thing you need to do is, what's the lowest to the highest numbers you have? The lowest is 21. The highest is 38. So here's what my brain is thinking over here. It's thinking, okay, 38 minus 21 is 17. I need to have at least 5 bars of my histogram. So if I've divided this by 5, I'm getting somewhere like 3.25. So maybe I should make this thing, these bins 3 numbers wide. Okay, so then that's what I'm thinking. So I have at least 5 bins. All right, so let's do this. First of all, I'm not going to start at 0. I'm going to draw me some little squigglies because I'm going to start probably at 20. All right, what's your next bin going to be? 23, and then 26, 29, what's next? 32, 35, 38, okay, and so on. Okay, now, let me refresh your memory about this. See this line right here? Something that goes in this bar here, which that's just an example, contains things from 23 up to 26. Not including 26. 26 occurs to the right of this number on the number line of 26. Okay? Now, this is actually a different, this is going to be interesting to me because I used bin widths of 4 all day long, and so I want to see how this changes if I use a bin width of 3. So let's start doing this. 20 up to 23. How many go in there? 20 up to 23. How many go in there? Looks like just that one. Okay. So I've got to draw me a little bar. That's 1. Okay. 23 up to 26, but not including it. So what's one do? 23. It's like this one. Is there any more? That's it. Okay. All right. So we got 1 again. All right. Okay. 26 up to 29, but not including 29. So what do we got? There's a 28. Oh, a 27. Oh, okay, 26. All right. So we got 3. Okay. 29 up to 32. So that's a lot. Is it 8? Okay. Okay, 32 up to 35. Thinking it's 6. What do you think? Okay. All right, and then 35 up to 38, but not including 38. So that's 1, 2, 3, and then I'll put 1 in that last one. So here I am at 3, and then 1 right here. All right. So what do you could you say? Do you think that your mean is going to be significantly affected by the shape of this data? I think, and you have to notate to the reader that this looks pretty unimodal, and this looks somewhat symmetric. And there does not appear to be any outliers. No outliers. So I'm feeling good about this data. I don't think it's crazily impacting the mean that I have to worry. So therefore, in conclusion, I say that nearly normal model applies. Okay, and you do not you want to emphasize that you know it's not perfectly normal. Okay, ta-da! P, H, and A are done. What's next? Again of a test for this one. Oh, not a 1 proportion. 1 sample. T test. 4 means. Okay, so that's P, H, A, and N. What comes next? T. What does that stand for? What does the T of a phantoms model mean you need to get? Your test statistic. Our test statistic for these are the t-scores. The others was a z-score. So it's x bar minus mu over standard deviation of the sample over the square root of n. And so, what's the x bar? What's the standard deviation of the sample? Ah, they don't tell us here. They just give us the data, so we have to calculate it. Actually, it's not too difficult. We are going to allow our calculator to give us this because we certainly do not want to have to calculate the standard deviation by hand. So here's what you do. You go stat edit so that you can put into a list. And I'm just going to kind of show you this just so we can save time. Okay, so just kind of mentally go through doing this. So we've got that right there in the list 1. So I want the calculator to calculate some information for me on this list. So I'm going to stat over to calc, and what do you think of that I'm going to use? 1 variable statistics. Number 1 variable statistics, it defaults to list 1. So calculate that, and voila, you get your information you want. X bar is 31.04. S of x, the standard deviation of the sample, is 4.25. So, yay. So let's finish this out. 31.04 minus the mean of 30 over 4.25 over the square root of n, which what was the size of our sample? 23. Okay, if you do this, you get 1.174. Ta-da! Okay, so now while you're finishing copying that, I just want to mention to you, remind you of what this is physically saying. 1.174 is a representation of what? The number of standard deviations you are above the mean. You're on the right track. My sample is located 1 and then 0.174 standard deviations above the mean. So here is the sample mean that we got when we collected 23 pieces of data. Okay, that's what that's saying. Now, what's the p-value? P-value is technically what is it? It's a probability of doing what? Of getting this sample here, or something more extreme, if the null is located there at 30. Very good. If the null is true, okay? That's the brown-eyed girl. Probability of getting this sample or something more extreme if the null is true. So let's get our p-value. I'm going to put this into my calculator. T, C, D, F from the lower t-score, the lower t-score out to infinity t-scores, comma, how many degrees of freedom? 22. So calculator, go check out the t distribution for number 22 and compute it. And the calculator will go do that, and it'll come up with 0.126. So, my p-value of 0.126 is greater than alpha 0.05, and so therefore my conclusion is to fail to reject the null hypothesis that says the mu is 30 miles per hour. I'm kind of putting this right here because I still get some people making wrong conclusions, and I wonder if you wrote that there, if it would help you. I don't know. So let's do our conclusion that we start. Since the p-value is greater than alpha, what are you going to do? I failed to reject that, and then you restate this. That the what? Okay, average miles per hour of all cars driving on Thomas Lane is 30. So do I have evidence to take to the city council that the average is greater than 30 miles per hour? No, I do not have evidence that the average of all is greater than 30 miles per hour. So what do you do as a resident? Are you going to go now retake a sample until you get one that gives you the answer you want? No, you can't do that. Now, does that happen? Probably. Okay, but that's not supposed to be done. Okay, I would like for you to just try one of these by yourself. It's data set number 1. I just want to make sure you can make a histogram. So let me get you to practice this histogram right now on your own just to make sure you're solid on that. I want to tell you there's an issue. This was supposed to be 180. So add a 1 in front of that 80. It's supposed to be 180. So make a histogram for data set 1, and let's see if you can do that on your own. Pretty much, yeah. So, let's kind of discuss this. So what happened was I chose, because this range was 130, I divided it by 5. I got about this. So I chose to make mine 25. And it looked okay. It's not beautiful, it's not perfectly unimodal and stuff, but the reality is, if it wasn't for this little chunk right here, it would look pretty good. It would look pretty unimodal, and then what else do we say? Somewhat symmetric, and what else do we say? That there are no outliers. Okay, so that's our conclusion. And now why it doesn't look perfectly symmetric because of this taller bar I have over here on the left. Do you think that this is enough over here on the left to significantly impact the mean? I mean, I think it's going to pull it down a little, but I don't think it's going to be a significant impact. So this here is not really going to worry me on like crazily influencing my meat. You will have something very blatantly obvious that will be wrong. Something like, you know, that might look like this, and then you even have an outlier over here. I mean, something like that, it will be made to you to be obvious to not work. Okay, so if you're not having something too crazy, it's probably, you know, maybe a better bin width would have made it nice for you. Okay, so that's done. So therefore, on your homework, what you are going to do is on your homework part 2, you just do numbers 1 through 4 because the last page we will save for tomorrow. All right, and numbers 3 and 4, by the way, have histograms you need to make.